Please proceed. Yeah, thank you.
And we can always pursue such problems as part of your project, right? So these interactions. Okay. Okay. In fact, one of the most some of the interesting MTech projects came from such discussions, right? See, obviously, if you and I knew the answer, right, we would have already solved it, right? So we learn the fundamentals and then use that to solve these tough problems, right? So
So,
yeah.
for example, we try to work it out in Lotus and Adams, but then the
Uh,
geometry doesn't really align always. So, with
yeah.
respect to two different types of vehicles, I just wanted to know whether there is a hardcore, standout relationship that this is how it will vary as a, guideline or something. So that's the main reason I just wanted to know.
I would say one needs to evolve that guideline, right? So by experience and analysis, that will be my first cut response. Like so. Yeah. So,
Got it, sir.
yeah. Okay, great. Like I think thanks for that discussion. So let's get started with today's class. If we recollect, yesterday we were looking at. Oops, what happened? We were looking at stability, right? We were looking at the fact that if you and I want to ensure stability or Bibo stability of the class of systems that we are studying, all poles of the transfer function should lie in the left of complex plane, right? So then, like even if one pole lies in the right of complex plane, we have an unstable system, right, or an unstable response, right? So we closed with the question as to what happens if we have poles lying on the imaginary axis, right? Because that can always happen. So once again, we are going to start with an example. By now, all of us know the process, right? So we are given a system. You and I take the Laplace transform with zero initial conditions. We get the transfer function, and then like once we get the transfer function, we will essentially get the response, right, for a specific input by calculating y of s and taking the inverse Laplace transform. So we follow the same process here. So the system that you and I are given is y double dot t plus y dot t equals u of t. We take the Laplace transform, we get this equation. By now we know how we get it. And then we apply all initial conditions to be 0. So then we get the Planck transfer function to be 1 divided by s times s plus 1. Right? So this is something which is pretty straightforward. Now, if you look at this transfer function, the value of n is 2 and the value of m is 0. Right? So the numerator is of order n, so n is 2. The denominator is only a constant term, so m is 0. Right? And what are the poles? We solve for the poles by solving the denominator polynomial to be equal to 0. So you and I get the poles to be 0 and minus 1. Okay, so that's what we have. So consequently, those are the two poles. So now, if we locate the poles on the S plane, what's going to happen is that, as we know, we locate a pole by using a cross mark. So one pole is at 0, one pole is at minus 1, right? So these are the two poles. Now, what can we observe? We readily observe that one pole is on the imaginary axis. Why? Because the origin is on the imaginary axis, right? And so consequently, one of the poles is on the imaginary axis, right? So now, given this, if you and I want to evaluate the step response, right, as a consequence of a pole being at the origin, okay? So some people will call this s equals 0 as the origin in the complex plane, okay? So we have one pole at the origin. So let's say you and I want to calculate the unit step response. We know that u of t is 1 and consequently u of s is 1 by s. So we find y of s and we do partial fraction expansion. Okay. So when we have a repeating term in the denominator, or we have a square term in the denominator, what we do is that, like for example, we have 1 by s squared, right? The way we take partial fraction is that, like, we do a by s plus b by s squared. Okay, so that's why that's how we do it, right? So this goes to the general theory that for any what to say denominator factor, the numerator term should be one order less. That's what this intermediate step would have taught us, right? So this is the standard way of taking partial fraction expansion when we have a square term in the denominator. Then if you and I process this and take the inverse Laplace transform and calculate the residues and then do complete the partial fraction expansion and take the inverse Laplace transform, we finally end up with this particular output, right? Where y of t becomes minus 1 plus t plus e power minus t, right? Now we can see something interesting. Okay.
Sir, just one question I have.
Please go ahead.
In one of the example in previous class, I noticed there is suppose this is example ys equal to 1 by s minus 1 by s plus if suppose there is a 1 by 2s. So should we add it and then take the inverse Laplace, or should we do the individual inverse Laplace?
So if you have the same factor, you can process it, right? So if I understood your question correctly, let's say we have 1 by s, let's say
sir.
plus 1 by 2s, right?
Yeah, sir, correct.
Oh, yeah. I think you can add them and take the inverse Laplace transform, because please note, Laplace and inverse are all linear operators. Okay, doesn't matter whether you do it individually or you add and take it. It doesn't matter. Okay.
But if suppose if it is coming from the input response and coming from the free response, so
yeah.
in that case, should we do it separately, or that also can be added?
So if you want to segregate them for our own understanding to begin with, saying this is the free response, this is the forced response, you can see, I can see where you are coming from, right? So
sir,
let me go to an example, right? So where is that? So I'm just going a little bit up. Okay.
Sorry, but can you just reframe the question once again and then go to the solution?
This one, sir. This one.
We take this thing, right?
Yeah, sir.
So what our friend is asking is that, let's say we take this example, right? So what we have done, we had both an input and a non-zero initial condition, right? What happened was that we essentially had this 1 by s plus 2 term common, right? I think
correct,
that's your question, right? Now.
Correct, sir.
So I wrote it like this because I wanted to show it explicitly that which one is the free response, which one is the forced response, right?
Yeah,
so I wanted to communicate the physics to you, but you could have said, hey, look, I process it, this is 1 by 2 minus 1 by 2 times s plus 2, right? And then plus 1 by s plus 2, right? This is going to be 1 by 2 plus 1 by 2 times s plus 2. Now I take the inverse Laplace transform, I'll end up with the same answer. Doesn't matter.
Yeah, correct.
Right?
Sir.
I hope I have answered your question, right?
So we can do either way, right?
Yeah, absolutely, right? So
okay, sir.
I only did it separately to show you that, okay, some part of it is free response, some part of it is forced response, right? To explain that.
Okay, sir. Thank you, sir. Thank you so much.
But anyway, you notice that I have anyway added it, right?
Yeah, finally added, sir.
Finally I have added, right? So to get one composite response, right? So
yeah, correct, sir. Okay, sir. Thank you, sir.
Welcome. So yeah, let's go back. But please note, when you and I are dealing with transfer function, by default we are assuming initial conditions to be 0, right? As I mentioned, why we will learn later, right?
Okay,
so what will happen if I have 0 initial conditions? What is the impact? We will learn as we go along. Okay. All right. So coming back to this example, we can observe that the unit step response of this system, which has a pole at the origin, is going to be minus 1 plus t plus e power minus t, right? Now we see something interesting, right? We observe that y of t will tend to infinity, right? As t tends to infinity. So the output of the system is unbounded. So we can observe that the unit step input is a bounded input, right? I'm sure all of us agree, correct? So but then we can immediately observe that the corresponding output blows off to infinity in magnitude as t tends to infinity. Now, will you call the system as stable or unstable? What will be your response?
Unstable, sir.
Unstable, right? Okay. Any other thought?
So it should be stable only, right? Because t tending to infinity is what we are talking about.
But what is the definition of Bibo stability? The output should be bounded in magnitude for all time, right?
Okay.
For any bounded input, right? So by that, see, in this example, it's very clear that the output is blowing off to infinity as t tends to infinity. Okay, that's very clear. Now the only point is that whether does it make it stable or unstable is a question. That there the answer is tricky. Okay, so that's why I asked this question. So one can have two different perspectives. What are these two different perspectives, right? So let's go down. Same system. Okay, now we are going to consider u of t to be sine of t, right? I think as discussed in yesterday's class, please note the Planck transfer function is a characteristic of the system, right? The input changes, that means the output will change, right? The Planck transfer function is fixed. Now, same system, we have essentially changed the input to u of t to be sine t, then u of s to be 1 by s squared plus 1. So consequently, y of s becomes this, and then we do a partial fraction expansion. So here you can see that the partial fraction expansion of 1 by s squared plus 1 is cs plus d, because s squared plus 1 is a second order polynomial. The numerator will be a first order polynomial, right? Some cs plus d. That's why we do it. And then if you and I evaluate it, I leave that as an exercise to you. You can I'm sure you would have figured out how to do partial fraction expansion by now, right? See, as I told, as the course progresses, I want all of us to become experts in partial fraction expansion, right? Before even I can finish writing, you should tell me the residues. That's how thorough we should be, right? So essentially, if we do the partial fraction expansion and take the inverse Laplace transform, this is what we get for y of t. Now, let's look at this. What are the terms that we have? We have 1, which is anyway a constant. We have e power minus t. I'm sure all of us know that e power minus t will tend to 0 as t tends to infinity, right? Then we have cos t and sin t. What can I say about the magnitude of cos t and sin t for all time?
Finite.
Finite, right? The
Varies between -1 to 1.
Very good. The magnitude of cos t and sin t will always vary between -1 to 1 for all time, right? So it is finite in magnitude. So now we see something interesting, right? Same system. What was the system? The Planck transfer function was 1 by s times s plus 1, right? This was the Planck transfer function. So what I did was I took this, gave a unit step input, the output became unbounded, right? Now I give another bounded input, let's say sin t, the output became bounded, right? That's what we have observed. Now, what do I call such a system as, right? So should it be stable or unstable or somewhere in between? This is an interesting question to ask, right? So if you look at it from a very pure perspective, right? As far as Bibo stability is concerned, what is the definition of Bibo stability? The output must be bounded for all possible bounded inputs, right? And for all time. Then the system is said to be Bibo stable. So I may have 100 bounded inputs in the world. I'm just taking 100 as a round number, right? Let's say for a system, I may have output to be bounded for 99 out of the 100 inputs. But if the output is unbounded for one bounded input, would I call the system as unstable? By the definition, yes, unstable, right? But it is not so unstable as before, right? See, if you have a pole in the right of plane, correct? The output is going to be unbounded for all bounded inputs. That's what we observe. Doesn't matter what bounded input you give, the output will blow off to infinity in magnitude. On the other hand, when you have what are called non-repeating poles on the imaginary axis, like what we did, the output is going to become unbounded only for specific inputs, right? For that reason, in such scenarios, we call the system to be critically stable or marginally stable, okay? So it is not stable, but it is not so unstable also. So I hope you get the point, right? It's somewhere in between, Okay, that's why we give a different term. But would we want such a system in practice? Certainly not, right? You and I don't want to design such systems. Why? Imagine a vehicle suspension being like 1 by s times s plus 1, and just for the sake of argument, right? Let's say vehicle suspension transfer function is this. So the car body displacement is the output, right? And the tire displacement is the input. Imagine that we go off on a like sidewalk. That's like a step, isn't it? Or into a pothole. Correct? By this derivation, what will happen? We will be thrown off. Right? Correct? Is it not? Correct? So the suspension will get torn and the vehicle body will be torn off in one direction and we will be torn off in one direction. I'm just taking an extreme scenario, just to drive home the point. So obviously you and I don't want such systems by design. We will ensure that. But sometimes the systems can be like that. See, for example, do we get such a second order system? Sort of like energy absorbing element, like a spring. See, if you take a mass spring damper system also, the spring is removed, right? You have a mass and a damper. You don't have an energy absorbing element. You will get such dynamics, right? But in practice, you and I are hardly going to encounter this. I just wanted to point out, okay? So this intuition we should have as an engineer, right? So that brings us to the summary, okay? And from this summary, I am going to give you some homework problems for the second homework, right? So that like we complete our understanding, okay? So let me go through the summary and then we will have discussions, right? Because there are many subtle points here, all right? So the first point is very obvious. All poles in the left of plane, okay? The system is bifostable. This we have understood by now. And some people will call bifostability as asymptotic stability. They're not really one and the same, but these terms are interchangeably used. Okay, this is just for our information. Okay, that's point number one. Now, even if one pole lies in the right of plane, the system is unstable. Okay, that is also known to us, right? And the main point, drive home point that, or the point which I want to drive home, is the fact that even if I have one pole in the right of plane, the system is unstable and the system output is unbounded for all bounded inputs. Okay, the keyword here is all. Okay, you give me any bounded input. If I have one pole in the right of plane, the system output will blow off to infinity. Okay, that's why it's unstable. Okay, now if we have non-repeating poles on the imaginary axis and no poles on the right of plane, like the example that we saw, right? See, in the example, what did we see? Like what did we encounter? We had the S-plane, right? I had a pole at the origin and then I had a pole at -1, right? So there's a non-repeating pole at the origin, right? It appeared only once. Those are what are called simple poles. So if we, see the adjective in the context of poles and zeros, right? In general, in the context of roots of a polynomial, simple roots means they don't repeat. Okay, they appear only once. Okay, as roots of a polynomial. So simple poles means it appears only once, right? If you have non-repeating poles or simple poles on the j omega axis with no poles on the RHP, the system output is unbounded only for select inputs. Okay. So what are these select inputs? We just saw that, right? When we have a non-repeating pole at the origin, then the system output is unbounded only for a step input. Okay. If you have u of t equals 1, the system output is unbounded. For any other bounded input, like sine omega t, cos omega t, the system output is bounded. That's what we saw through the example. Similarly, we can also have a situation like this, right? I may have a situation where in the S-plane, I may have a pair of poles at plus j and minus j. See, for example, if my plant transfer function is 1 by s squared plus 1, right? So this is like a mass spring damper system with no damping, just a mass and a spring, right? So if I don't have damping, what will happen is that the denominator polynomial is s squared plus 1. And if I solve s squared plus 1 equals 0, I will get s to be plus j and minus j. Okay. So consequently, I have non-repeating poles at plus j and minus j, right? Is it not? So that those are what are called simple poles. Now, if we have such a case, it so happens that my output will become unbounded only for cos t and sin t. Okay, the angular frequency of the sine and cos wave, cos signal should be equal to the angle magnitude of the pole. Okay, which I have on the imaginary axis as complex conjugate poles. See, what is the magnitude of plus j and minus j? It is 1, right? So cos omega t and sin omega t, I substitute omega equals 1. Only for those inputs, the output will blow off to infinity. For any other bounded input, let it be step input, cos 2t, sin 2t, cos 3t, sin 3t, like that, right? The output will be bounded. That is the important result. So in general, if you and I have a pair of non-repeating poles at plus or minus j omega, like the case that we saw, and omega is not equal to 0, and no poles in the right of plane, the output is unbounded only for sinusoidal inputs having an angular frequency of the magnitude of the pole, omega, right? Sin omega t and cos omega t. That is a very important result. Okay, I hope the subtle point is clear. Now, the fourth case is the following. If you have repeating poles on the j omega axis and no poles in the right of plane, the system output is unstable for any bounded input, right? A system output is going to be unbounded for any bounded input. The system is going to be unstable. So what do I mean by that? Let us say I have a system whose transfer function is 1 by s squared times s plus 1, right? What will be the poles? It will be 0, 0 and minus 1, right? We are going to have a repeating pole at 0, right? I hope everyone understands, right? So everyone agrees with me. In the denominator, we have a s squared term. So I'm going to have a repeating pole at the origin. If that happens, and I plot the S-plane, what I'm going to have is that I'm going to have 2 poles at the origin and 1 pole at minus 1. So here we have a repeating pole at the origin. If you and I have repeating poles on the imaginary axis, right, and no pole in the right of plane, the system is unstable. Okay, no matter what bounded input we are given, the output will always be unbounded. Okay, so that is the fourth case. Okay, so these are the 4 cases. So let me recap before we open up for discussions. So because this is an important concept. Okay, I want all of us to understand this very, very clearly as we go ahead in the future. Point number 1, case number 1, if we have all poles in the left of complex plane, strictly negative real parts, right? Nothing on the imaginary axis, nothing on the right of plane. We have the best scenario. System is stable. Okay, no doubt. Now, even if one pole lies in the right plane, system is unstable, gone. Okay, the system output will be unbounded for all bounded inputs. That is the second case. Now, if you have non-repeating or simple poles on the j omega axis with no poles in the right of plane, like system output will be unbounded only for select bounded inputs. So if you have a non-repeating pole at the origin, step input will result in unbounded output. But sin omega t, cos omega t for all omega will be bounded. Okay, we will have bounded output. Similarly, if I have non-repeating pole at plus or minus j omega, right, step input will give me bounded output, sorry, and all sinusoidal signals whose frequency is not omega will also result in bounded output. Only for sin omega t and cos omega t will my output blow off to infinity. Okay, so that's the third case, right, where the system becomes marginally or critically stable. Okay, then the fourth case is that we have repeating poles on the j omega axis and no poles in the right of plane. The system is anyway unstable. Okay, that is, the output is going to be unbounded for all bounded inputs. Okay, that is the fourth case. All right. So with this in mind, I am going to propose homework number 2 for us. Right. So what is homework number 2? We consider the system whose governing equation is this. Okay. So I did the case where y double dot plus y dot equals u of t. Now we have to do y double dot plus yt equals u of t. So if you derive the Planck transfer function, we get 1 by s squared plus 1, right? This is exactly the case which I discussed now, right? So you already know the answer. I only want us to figure out the answer, right? So where are the poles? The poles are at plus j and minus j, okay? Non-repeating poles at plus j and minus j. I want you to find y of t for u of t to be 1 and u of t to be cos t. Obviously, from the result that we learned, when u of t is the step input for this particular system, the output will be bounded, right? But for u of t is cos t, what do you think will happen to the output? It will become unbounded. Why? Because the magnitude of the pole is 1, right? Magnitude of poles is equal to 1. So for any sinusoidal input whose angular frequency is equal to the magnitude of the pole, the output will blow off to infinity. And that means cos t and sin t will result in the magnitude going out of bounds, right? So that's what will happen. All right. So this is just, we are just convincing ourselves. So such cases where we have, like non-repeating poles on the j omega axis with no pole in the right of plane is what is called as a critically or marginally stable system. Okay. So for this particular reason. Okay. So we are just reinforcing our understanding through the first problem in homework number 2. What is the second problem in homework number 2? Second problem in homework number 2, I want us to understand the effect of zeros. See, we understood the effect of poles, right? What is the impact of poles on the system response, right? The poles come as exponents of the exponential term, right? The location of the poles influence stability, right? That you and I have understood. Now, what we need to do is that, like, the natural question is that, hey, what will zeros do, right? That is a natural question, right? Is it not? So, to answer that question, I am proposing this problem. So, please note that we would have already done the problem y double dot t plus 3y dot t plus 2y of t equal to u of t, right? So, we have already solved this problem and obtained the unit step response. Now, what I am doing is that I am changing right hand side. What am I doing? I change the right hand side as u dot plus 3ut. Left hand side remains the same. So obviously what will happen is that the numerator of the transfer function will change. So there will be a 0 in this problem. I want you to calculate the unit step response, compare. So compare with the unit step response of this system, okay? And then state your observations, right, on what is the impact of the 0 on the system response. I hope these two problems are clear, right? We are reinforcing our understanding of what happens if we have a non-repeating pole on the j omega axis, right? In the second problem, you and I are studying the influence of a 0, right, on the system response.
So will there be a stability wherever there is a 0 occurring? So
stability is only linked to the poles, right? So in the second example, the poles are the same, right?
I'm just trying to guess, sir. Sorry.
Okay. So yeah, please do the problem, right? I think you will observe something interesting, right? So yeah, so that's a good point. See, this is what I want us to learn, right? So when do we learn the best? When we do it on our own, right? That is why I'm teaching the fundamental concepts and then leaving some problems to you as homework, but we'll come back and discuss, right? So, so our friend took a reasonable guess, but my response to that guess is that, like, the poles are the only entities which influence stability. Okay, I will give you the answer. Okay, zeros essentially impact the dynamic response along with the poles, right? So the system will still be stable because the poles remain the same, but now you will see a difference in things like the steady state value, other aspects of the response, right? Please do it, okay? Compare. Then I'm sure you will come back in the next class and say, hey, it's very simple, like it is very obvious, right? So I think we will figure it out, right? I hope second homework is clear, right? And as we discussed, please keep solving these homework problems kindly do not solve them in a book. Please solve them in separate sheets. Write the homework number with your name and roll number. And as we discussed, you can submit the homework in person when we meet for the midterm exam on March 23rd, right? Am I correct? We agreed March 23rd, right? Yeah.
Yes, sir.
Yeah. When you come here in person for the midterm exam for this course on March 23rd, you can submit as many homeworks as we have done till then. Okay, that's what we will do. All right? Fine. Okay. So this is the content for this course. This class. And this is a homework problem for this week. Okay. So see, the idea of also from my end is to not give too much of there is too many problems as homework, right? At the same time, we learn a concept, we do a homework problem to reinforce our learning, right? Like that, we do continuous learning, and there is no time pressure on us, right? The homework assignments are uniformly distributed over the semester, right? Fine. Okay. Now questions, discussions, please. Next slide.
Professor, sir, I have a question regarding the 4 type of stability we have seen while key takeaway that you have shown to us. Now, sir, like for example, I am trying to design one subsystem. Suppose maybe it's a braking system, or maybe it's a steering system, or maybe it's something like that. So, in which category I should put those system, like category 1, 2, simple pole, or maybe, of course, it should not be, what I mean to say, unstable, unbounded in that way. But between the I would say semi bonded or pure bonded in that sense. So, like for example, suppose if I'm designing a particular component or subsystem, whether I should keep in that range or this range, how we can decide in that sense? I'm sorry, it's a stupid question, but I'm still asking.
No. I think all questions are helping us learn. As I told in the very first class, I think as I shared with you, I've been doing a lot of programs for the automotive industry for the last 12-13 years, right? And also been part of this MTech. It's been a rewarding experience for me. Because we get different perspectives, right? So from your perspective, what I understand is that, if I have to design a system, let's say suspension, steering, brake, powertrain, whatever I want, right? So what category should I ensure? My answer will always be the same, the first category. So if you and I have the power to decide, all systems should be stable, right? Is it not? Correct? So if you have the power and ability and the freedom to tweak the system parameters, you always make it stable. And we will see that these concepts are going to be useful in vehicle dynamics. See, once again, I'm teaching you all the mathematics, the fundamental theory. See, I think kindly bear with me for the first few weeks, because we need to learn these concepts, right, to understand the finer points of vehicle dynamics, right? So even we will use these concepts when we look at lateral dynamics, right? In lateral dynamics, we would have heard about understeer, neutral steer, oversteer, and vehicle losing yaw stability, spinning out of control, and so on, right? Vehicle losing yaw stability has to do with poles going to the right of way. Okay, we will see that when the vehicle operates, depending on the speed of the vehicle, right, the poles of the system transfer function can migrate into the right of plane when the vehicle is in a state of oversteer. Okay, and the moment the poles migrate to the right of plane, the vehicle spins out of control and yaw stability is lost, right? So I hope that sort of connects the dot to your question. So if I'm a steering engineer and I want to look at the vehicle cornering response, I better design my system such that I never hit a condition where my poles migrate to the right of complex plane due to operation, right? So then I retain cornering stability, but it's easier said than done, because our vehicles operate under such a wide range of operating conditions, right? We have dry roads, we have wet roads, oily roads, slick, muddy roads, icy roads, and so on, right? So things change, right? We have to live with it. That's where now you can see why active control becomes important, right? All the electronic stability control programs and like other tools come into play, right? Because sometimes the response may become unstable, right? We want to retain it as stable. Okay, that is why today's concept is very important, right? At the heart of many of these vehicle safety systems, right? ABS, ESP, and so on, right? Lies the notion of stability. They intervene when the system senses that the vehicle response is going to become unstable. It pulls the vehicle back into stable regions. Okay. Yeah.
Thank you so much, sir.
Yeah.
Sir, am I audible?
Please go ahead.
I just couldn't help but notice that all our functions are continuous functions and they are mostly differentiable also.
Yeah.
Within the given range of inputs and outputs. So we are talking about the outputs, but we are not telling whether it is local output or a global outputs, meaning local maxima, global maxima, or all those aspects. So with respect to the system's response also, so how will this be correlated in the sense when we are saying that there is a particular value at which a function is becoming zero or it is getting a solution, that means that it is entirely that way or it is just a local solution.
So, I think that's a good perspective. If I can paraphrase your question, right, based on my understanding. See, we talk about these global optima and local optima, if we are having a function of a variable, right? For you and me, we are talking about functions in terms of time. See, there are two aspects. See, let's recollect fundamentally. Fundamentally, you and I are dealing with dynamic phenomena where the input and the output are functions of time, okay, period, right? It's just a mathematical construct that we have moved to the S domain, and we have functions of S where, continuity is lost when, when we hit the poles, and, we may have what are called singular points there, right? But ultimately, you and I need to focus on the, time response, right? So there, we are going to have a continuous response, right? Because we are dealing with physical systems, which essentially processes even sudden inputs. See, even if you take a car going over a pothole, right? Yes, it is a sudden input, but the system responds to it and the output is more gradual. Yes, it may be harsh, but we are not going to be blown out, right? So I hope I'm able to convey my thought process, right? So we are not going to have this notion of global optima, local optima coming when we are dealing with functions of time for our purpose of study. Let me put it that way, right?
Clear, sir.
Mm-hmm. Okay. Any other questions?
Sir,
Please go ahead.
sir, you said that marginally or typically stable, that is also comes under unstable category. So once it is coming under unstable category, like once it is unstable, system is unstable for us.
Yeah.
Yes, sir.
Please go ahead. Please go ahead.
So why we are studying this separately and connecting to that means if we can connect with the means physical object, it will give us some more clarity, sir.
Very good. I think that's a good point. So in fact, if things were left to me, I will call it unstable. Okay, but then unstable in the Bibo sense. So things are complicated by the fact that there is another notion of stability. Okay, what is called as stability in the sense of Liouville. I will not get into that right now. So I think one of our friends raised this point in one of the earlier classes, right?
Yes.
About trajectory tracking and so on, right? Asymptotic stability. If you search in Google, asymptotic stability means, the vehicle comes back to the trajectory and so on, right? That's the definition you could find out, right? And we had a discussion, right? So now your point has to do with it, right? So let me take that same example. So in fact, when we go to this stability of what is called as an equilibrium state, I even took the example of a pendulum, if you recall, right?
Correct.
I hang a pendulum from the top and let's say I tap it, right? So the pendulum keeps on oscillating, but then like it finally comes to the vertically downward equilibrium state because of friction, air friction. Now let's assume for the sake of argument that you and I are in vacuum, no air friction, right? I go tap the pendulum. What will happen to the pendulum?
It will not stop.
It will not stop. It will keep on oscillating indefinitely, right?
Correct.
Would
Right.
you call it stable, unstable?
It will be unstable.
Well, I would say it is stable, right? Because it's
Okay.
close to the equilibrium state, right?
Yes,
That's
yes.
where now you get the point, right? Your question is very
Yes.
good, right? Now we are
Yes.
getting a matter of perspective, right? So what
Correct, sir.
I think more than stable, unstable, the appropriate question to ask is that is it acceptable or not acceptable? Okay.
Mhm,
And
mhm.
it's a better question for engineers, right? For mathematicians, it's stable. And it so turns out that when you have these simple poles on the imaginary axis, it is stable from the sense of equilibrium state, but it's unstable from the sense of bibostable. So depending on your notion of stability, we have two different answers, right? So a good via media is to call it marginally critically stable and differentiate it from the unstable case, right? But is it desirable? Certainly not, right? That's why I took that example of that suspension system, right, to communicate it to you. All right.
Yes, sir.
So that's where like I wrote both the terms so that you can form your own opinion, right? I'm not going to suggest one way or the other. Yeah, if you look at it from the perspective of bibostability, is unstable, right? But it's not so unstable also, right? Yeah, like the pole lying in the right of complex plane, right? So yeah, it's somewhere in between, right? And it's stable in the sense of Lyapunov, right? So stable from the sense of what is called as stability of an equilibrium state. So that's why we make a differentiation there. Okay, yeah. But you and I
Yes.
do not desire it in practice. Let me make it very clear. Okay, if we have a system like that, we do closed loop control to remove that pole from the origin. Okay.
Okay, sir. Sir, what I'm understanding is like whether this has to be accepted or not. That will also sometimes depend on the
So
input we will be getting.
yeah, once again, it depends on the application and the perspective, right? Is it not? See, if we have these poles on the imaginary axis, even though they don't repeat, I may tell that hey, only for one particular class of inputs, the output is going to become unbounded. But your bad luck and my bad luck, if we encounter that in practice, what will happen? Right? Correct. So, would we
Yes.
be able to get the product approved? Certainly not. Right. That is why.
Understood.
No, like in response to another question asked by one of our friends, I told that if the choice were left to me, I will always go with option one. I will tweak something to make it option one, right? Stable.
Correct.
But
Correct.
See, life is not very simple, right? Sometimes you and I are given systems to work with which may fall in these categories. That's all I'm communicating, right? Yeah.
Understood, sir. Thank you, sir.
Yeah, welcome. Yeah, I think because that we are close to finishing. Yeah, questions, please.
Sir, just a small request from my side.
Ah.
So maybe in the next class or going forward, before giving those examples or anything, if possible, can you just say whether this is a equation which describes any automotive system in practice? So it is better to
sure.
correlate and understand.
Sure, absolutely. See, for example, second order systems are going to come in suspensions, right? First order systems are going to be characterizing brake system model, powertrain models, and so on, right?
Yes, sir.
Second order systems once again will characterize lateral dynamics, right? When we deal with cornering, we are going to see all those things, right? Absolutely, right? In fact, if you scroll down the video, yeah, if you just have some time and if you're curious, go downstream, you will see all these equations coming. But the only thing is that the equations are going to become a little bit complex.
Yes, sir.
It's not like going to be as simple as what I'm writing here. We just start off with simple stuff so that you and I can become comfortable, right?
Yeah, I understand that you are doing quarter car model and all those things down the line in the lectures, but so I just wanted to know in beforehand whether it's easier to comprehend the equation that way. So
Second order models are going to come in suspension models, quarter car models, even cornering dynamics, bicycle lateral dynamics model, and so on, right? first order models are going to characterize braking models, powertrain models, right? Okay.
Thank you, sir.
Okay, so let me quickly take attendance. But before taking attendance, a quick announcement. Next week, we will not meet on Monday because I will be traveling for a meeting. Like some days, I think I have to go out of town for official meetings. So next Monday, I will be out of town for an official meeting. So next week alone, we will meet only on Tuesday and Wednesday. Okay, I will post it on the Google Classroom stream also. So consequently, you and I need to watch what videos, what are they? 4 and 5, is it? Where are we?
6.
Oh, we have already completed 6, is it? Okay.
Yes, sir. 7 and 8. Yes.
Yeah, 7 and 8. Fine. I am sorry. I am still in week 1. I'm sorry. Okay. So I think we have completed 6 lectures. So then we will discuss lecture 7 Tuesday and lecture 8 on Wednesday. Okay. We will not have a class on Monday. Okay. Fine.
Okay, sir.
Noted, sir.
Okay. So Aditya,
Present, sir.
Anand,
Present, sir.
Ananta Kumar,
Present, sir.
Arunachalam, no.
Present, sir.
Hassan, no.
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav,
Yes, sir.
XP Narayanan, no.
Present, sir.
Prabhakaran,
Present, sir.
Dem Vinayak,
Present, sir.
Rahul. Rahul? Is Rahul on the call? No.
Yes, sir. He was here, sir. He had some network issues, sir, I guess.
Fine. Okay. Sure. Yeah. Roshan? No.
Yes, sir.
Kabish?
Yes, sir.
Kapish?
Yes, sir.
Yes.
I don't know. Yes, sir. What is the planned activity?
Malish? No. Is Valish around?
No.
No, sir.
Okay. Vignesh?
Yes, sir. Present, sir.
Vigneshwaran?
Sir, present, sir.
Okay. Okay. Vijayaraj?
Present, sir.
And then Vikas?
Present, sir.
Ramanand?
Present, sir.
And you are on.
Present, sir.
Only Vinesh doesn't seem to be there, right? So then, thanks for attending.
Sir, before we close, a simple request. Basically, we had some discussion with our HR people.
I'm sorry. Can others please? I'm not able to hear. I'm sorry.
Sir, basically, regarding the exams, we had a discussion with our HR for other matters, sir. So I'm not in we are writing a mail to you, sir, regarding that.
Okay.
So it's just a humble request. The final discussion is with you only, sir. Just a appeal from our side. So I will not take your time. We are sending a mail to you, sir. Just if you can kindly have a look on that, it will be great for us, sir. Please.
So is it that you want to take it in your premises? Is it?
So what we have discussed with HR is what they are telling is ki final exams and all those things is fine. We can reimburse the expenses and all. But
Okay.
for the mid-sem and quizzes, it will be difficult for making a case because institute has given a information to HR that IIT has in principle agreed to take the exam offline also, online also in that way. So that was
Okay.
their point. So that's
No
the only thing.
So then, I have no issues. I will enable a hybrid mode, right? So because I think it's fair to discuss when everyone is here, right? So I am assuming that those who are in Chennai would want to come, right? And what we can do is that during the same time slot, you can write online. Absolutely no problem, right? So,
It's a very very thankful note for us. Thank you so much for that.
sure.
So-
Most welcome. Sorry. Yeah. So I think,
three people from us, like Vikas, me, and Ramanand.
I think the boss for you and me is Arunachalam, right? Yeah.
We have discussed with Arunachal sir. So
Okay.
Arunachal sir has told us to just make a direct appeal to Professor sir. So hence
No problem.
it is a request.
So see, before the exam, for me, exam is an opportunity to learn, right? And we are
Right.
all right? So we are going to write it professionally, no matter where we are. See, I preferred an offline meeting because during COVID we could not meet many batches, right? So it is always nice to meet in person and see each other's face at least, right?
Sir, actually,
right?
we are coming to Chennai for some official purpose. So it will be great if you can give us some time for 5 minutes to meet in that.
Sure. You can send me an email and we can fix up a time slot.
Sure, sir. Sure,
so
sir.
that was the motive behind the in-person exam. But if somebody has a valid constraint, please coordinate with Arunachalam, and I request Arunachalam to let me know at least a week before the exam who wants to take it online so that I can appropriately coordinate. My suggestion is that those who are in Chennai, I would request them to come in person. You know, like, see, you can also see the lab, department and so on, right? So yeah. Right?
So Chennai,
Sure, sir. Sure.
Chennai, we are coming, sir. We are coming to.
Okay.
Sir,
And,
for the final exams, we will definitely, we will be coming. So there is no
sure.
like.
Absolutely. Okay.
Sir, thank you so much. Sir.
Yeah, we
Thank
will
you
do
so
it that way then. Okay. Thank you. Bye bye.
Thank you, sir.
Thank you.
Okay, I'll
Thank
meet
you,
you
sir.
next Tuesday. Bye. Bye.
Bye, sir.
Thank you, sir.
Thank you, sir.
Welcome.
Thank you, sir.